Welcome back to Network Steganography. Today we will cover Chapter 5, Hiding Patterns. What are patterns? Patterns are a solution to a recurring problem in a given context. They are reusable and described in an abstract way, so it's not a detailed description, and we have something that reoccurs, a problem that reoccurs, and the solution is reusable, that we apply to solve this problem. The term was introduced by Alexander et al. In the late 70s for the domain of architecture. They described a so-called pattern language that comprised 253 different patterns, and an example of the patterns that they described could be the following. So if the problem is that we want to minimize artificial light, then the context could be to save energy, and the solution would be to build a window into the building to receive as much sunlight as possible in that room. Architectural patterns discussed in informatics are rooted in software engineering. Probably you already have heard of the Gang of Four. For instance, well known are user interface design patterns, like the vertical drop-down menu, which you can see here on the screenshot. Patterns can even be used to generate user interfaces in a semi-automated manner. So I think that's an interesting side fact, but this fact is not relevant for the exam. Security patterns are a separate term based on the definition of patterns. So they are described as follows. Patterns, first of all, are reusable packages incorporating expert knowledge. Specifically, a pattern represents a frequently recurring structure, behavior, activity, process, or thing during the software development process. So that's a software context, but if we want to add the security context, then we can take the security pattern definition that says, okay, a security pattern includes security knowledge and is reusable as a security package. Now the thing here is that one can describe at least two types of patterns in that context. So security patterns can basically be found at all levels of the software development lifecycle, and they can describe knowledge, techniques, and means to improve security. So that's the one hand side. But at the same time, there are also patterns that describe an attack. There's also the so-called cyber pattern, which is in gray here because it's not relevant for the exam, but they are linked between architectural and security pattern. A few comments on patterns. When I discussed this with the patterns research community, I wanted to know when is a pattern actually a pattern? I mean, how many times need the pattern to occur to be recognized as a pattern? So the agreement was it has to occur multiple times, and it seems that there's a general agreement by at least several individuals that the minimal number of occurrences is 3. So if something occurs only twice, then it's not really a pattern. Now, a next term that we need are pattern collections. They comprise patterns of a given domain, and they can be understood as pattern catalogs, but the latter is additionally searchable, for instance, using an index of patterns. We use both terms, collection and catalog, in the same way because the focus here is not so much on the construct and concept of patterns, but rather on information hiding. And we use patterns only as a means to describe hiding methods in a unified manner, but you will see this soon. So pattern collections could, for instance, comprise user interface patterns. But there's a problematic aspect, and that's the linkability of patterns between collections of different origin. So because if they are not described in a unified structure, it's hard to provide any links and compare patterns. This is why pattern languages have been introduced to solve the aforementioned problem. So they provide a unified description of patterns, and they also allow to build links and hierarchies between patterns, and also introduce aliases to prevent redundancies. For instance, if a pattern is known by multiple names, then you can choose one pattern name but also add the other names as aliases so that they are also taken into consideration. And one such pattern language is the PALML, the Pattern Language Markup language. And PALML is one example of such a pattern language. However, we use only a subset of PALML for our purposes. So PALML in version 1.1, which was originally used for describing network steganography methods, comprises several attributes like an identifier, a name, an alias, and so on. We don't need all of them. We just use a subset that I will show you soon. And usually these patterns are described using XML, but you can also have a textual table, for instance. But first of all, what is a hiding pattern? Hiding patterns were introduced in this 2015 paper here, and they describe the key idea of hiding techniques. So the description of a hiding technique here is not, for instance, protocol specific. It's abstract, kept on a non-detailed level. And also these patterns help cleaning up terminology and taxonomy because they can form the links, you can derive one pattern from another, and so on. So in general, we would say that, as mentioned, the pattern is a solution to a problem in to a reoccurring problem in a given context. And one could say that the solution for our problem would be a hiding pattern. So the problem would be we want to transfer information in a stealthy manner, for instance, the problem could even be more specific here. And the context could be a network protocol, a given network protocol, for instance. And then the solution is a particular hiding technique. However, this is not kept as core idea over the years. So because patterns were described in a way that they actually are not pattern protocol specific. So what we essentially use and what hiding patterns essentially use is just a subset of the patterns concept and also a subset of this PALML pattern language. Here's the subset of attributes that are used. So each pattern has an ID, a name, can have aliases, but that's optional. Can have an illustration of the application scenario for the pattern. It has a context that specifies the situation to which the pattern can be applied, which is actually used as a hierarchy indicator in our context, in our patterns taxonomy. So you say, okay, it's a temporal pattern, a timing pattern, so it describes a timing channel or a storage channel, things like that. Then there's the solution provided by the pattern. Evidence is linked to references in the literature, so to show that the pattern is actually a pattern because it's used multiple times. And then there can be additional literature references and an optional implementation description, like code. So a few hundred hiding techniques are known, and they hide secret information and metadata of network traffic. The problem is that we have an inconsistent terminology that I spoke about already in chapter 4, and that scientific reinventions were, for this reason, rather common. So instead of dealing with all these hiding techniques separately, and that's really a key issue here also from a didactic perspective, we only need to understand a few hiding patterns. because I mean you can either study these few hundred hiding techniques or the few patterns that are existent or known. So initially only 11 patterns were found and described, while 109 hiding techniques were analyzed that were published between 1987 and 2013. Later, more patterns were found. And some of the original patterns were also split into multiple patterns to have a more precise taxonomy. Yeah, so as mentioned, patterns can build taxonomies because also they can have child patterns, aliases, and so on. This is the original taxonomy from 2015, actually developed in 2013 and 14, comprising 11 patterns. So as you can see, we have some network covert channel main category, and that's divided into timing and storage channels. We have 4 timing patterns, and we divide the storage patterns further into those that modify payload, although this was excluded because payload of network packets was considered to be the domain of digital media steganography. So it's not really what network information hiding is about. And so this was excluded at the beginning. Later, this was included again, but I will show you this in a few slides. And then we have the modification of non-payload, for instance, header fields, padding fields, things like that, where we can either preserve the structure of data by simply modifying some attributes such as a random value in a field and so on. So we have 3 patterns here, one of which has 2 subpatterns, or we can modify the structure so that we alter the structure of the network packet. For instance, we can increase or decrease its size or add some redundant information. Again, we have one pattern here, the sequence modulation, that has 2 sub-patterns or child patterns. The latest version, as of 2029 summer, is this one. It comprises 16 timing patterns and 10 storage patterns. As you can see, the timing patterns were further divided into those that are protocol aware, so they need to exploit some semantics of the network communication protocol. They must be aware of the protocol's meaning, while other patterns are protocol agnostic. The structure modification and preserving aspects were kept, but as you can see here, the modification of user data was added. I will speak about this later. And also, as you can see, some patterns like PS20 are derived, as indicated by these arrows, from other patterns. So the original publication is what you already know, it's this one, and then this publication added a few more patterns and these protocol agnostic and protocol aware distinction. The payload-based modifications were added in this publication. Then in this publication here added a sub-pattern, the value influencing pattern, and these 2 publications added the latest timing channel patterns here, PT 15 and 16. Well, there's an official website for patterns, ih-patterns.blogspot.com, or just click on this link here, where you can browse the pattern collection and just click on some of the patterns, and then you get a description with the PAL-MAL tags, slightly modified version of PAL-MAL tags here, where you have evidence, context, and so on. Okay, let's go through all these patterns. Keep in mind that if you understood all these patterns, then you already understood the core concepts of a few hundred hiding techniques. We start with timing channel patterns, in particular the protocol agnostic ones, so those that are not really considering any meaning in the protocol. They are not aware of syntax or semantics necessarily. What are they doing? So the first pattern is the inter-packet times pattern, introduced in 2015 originally as inter-arrival times pattern, but inter-packet times is a little bit more generic. And so the pattern was renamed in the Wiley book. How does it work? Well, the covert channel alters timing intervals between network protocol data units, which are packets, frames, and so on, to encode hidden data, as you can see here. So packet 1 and packet 2, if the protocol gap is small, then it might be a 0-bit. If it's a larger time gap, then it would be a different bit, for instance. Examples, well, you can do this with basically all PDU types, be it Ethernet frames or IP packets. The message sequence timing pattern was introduced in 2016 in the Wiley book, and it's based on the idea that hidden data is encoded in the timing of message sequences. For instance, one could acknowledge every end packet received or sending some FTP command m times, things like that. So as you can see here for the example, if the covert receiver sends 2 packets and the covert sender acknowledges a packet, then the question is, how long does the covert sender wait till a packet is acknowledged? And the particular timing of a specific packet here would then represent the hidden information. Last of the protocol agnostic patterns is the rate throughput pattern, where the covert sender, this was also introduced in 2015 already, alters the data rate of a transmission. So here it's either data rate 0 or 1, and it is modified over time. So you have something like this, and you try to encode the message in that way. Of course, all these patterns are noisy channels. There are a few examples, like you could exhaust the performance of a switch to affect throughput of a connection from a third-party node to a covert channel receiver over time. This idea is a nice one, and the reference is found in, I think, this paper here. Or you could directly alter the data rate of a legitimate channel between the covert sender and receiver. So that would be the most trivial example, I suppose. Okay, next are the protocol-aware timing channels. For space reasons, I did not add PT 15 and 16 here. I just wrote more patterns because then it's hardly readable anymore. So the artificial message or packet loss pattern was introduced in 2016, but actually forked or derived from and replaced the original PDU corruption pattern. Actually, the PDU corruption pattern will occur on a later slide too. It was one of the patterns that was split into 2 patterns to make the meaning more precise. So artificial message or packet loss is a different thing than a plain corruption of data. So what is done here is that the covert channel sender signals hidden information via artificial loss of transmitted PDUs, like they send packet 1, packet 2, packet 3, and 4, but packet 3 gets dropped. And whether a packet gets dropped or not can then encode hidden information. You can do this, for instance, in either EEE 802.11 networks, but you can also do this between 2 VPN sites. Let's assume this is VPN site 1 and this is connected to VPN site 2. And there's some covert sender here that sends confidential data to this node, and only a direct communication is allowed. So there is no intermediate communication feasible. They are not allowed to communicate to outside systems, but let's assume here is a router. And that's the actual covert receiver. Then the covert sender could send selected packets to the destination, but it could drop selected ones, so the channel would work, and this way information could be leaked to the covert receiver. Then there is the message ordering, or former PDU order pattern, introduced in 2015, renamed in 2016. And here the covert channel encodes data with a synthetic PDU order. So for instance, some protocols like the IPsec authentication header or TCP have a sequence number that can be exploited for this purpose. So let's assume over time you send these 7 packets, and the covert sender either keeps the original order or it flips the order to indicate a hidden message. So if as you can see here, the order is kept, but here it's not kept, so the order is flipped. Again, this is of course a noisy channel, mimicking some typical network behavior, and again here order is flipped. Then the original packet, the original lost packet appears, but here should be packet 6, so again the order is flipped. You can encode this information in any way you want. You can also encode the bits here in the interpretation in a different way, as done here. This is just an example coding. The artificial retransmissions pattern is the opposite of one of the previous patterns, namely the one where we drop packets. It was introduced already in 2015, and here the covert channel retransmits messages to mimic, for instance, TCP reliability or DNS requests, which are often sent multiple times, because if you get no response, you just send the packet again. And also this can be done by just not acknowledging a packet and forcing the covert sender to resend the packet. So this is also feasible. And here, as you can see, some packets get duplicated, others are not. Then there are frame collisions. So this is also forked, as mentioned. There is a second pattern forked from the original PDU corruption pattern, and that's the frame collisions pattern. And so the idea is you cause artificial frame collisions in a multi-access, in a network with medium access control, and the capability to detect collision. So as you can see here, sometimes we have a collision, and in other cases we don't have a collision, and this allows us to indicate hidden bits. Of course, you can do this in the typical environments like carrier sense multiple access collision detection exploitation using jamming signals or similar mechanisms for collision avoidance networks. Then there's the temperature pattern, which is actually considerable as an indirect pattern, and it's one of the most rarely used patterns. So a covert sender influences some intermediate node's clock screw, which is then inferred by a covert receiver. So this is not a pattern that is using a direct communication, because you need to influence some intermediate node in any case, or an intermediate component that might reside on the covert receiver, but it needs to be influenced. Then there's the artificial reconnections pattern, where usually multiple nodes are connected to a central element, such as Wi-Fi clients, which are connected to an access point, as you can see here in this figure. And depending on which existing connection gets a forced reconnect, a secret message is transferred. So we have shown for Wi-Fi networks that the covert sender can trigger disconnects in Wi-Fi, forcing the clients to reconnect. And let's assume this client represents the letter A, and this is the B, and this is C. Now, if clients 1, 3, and 1 would be forced to reconnect, then the message would be AB, ACA. Also works for MQTT environments. Rather similar pattern is the artificial resets pattern. Also a rather new pattern. It's relying on traditional mechanisms, but it was not studied earlier in the network information hiding context, and the paper here from the Detonator workshop will be published in November 2021. So the idea here is that the covert sender triggers a connection or state reset, while the covert receiver needs to monitor it. So for instance, one could send a reset packet using a classical TCP reset attack to reset a client by spoofing a TCP segment. Or in the constrained application protocol, which is a typical IoT protocol, this works as well. The covert channel can trigger resets there as well. This can be achieved when the message is embedded by sending an empty non-confirmable message to a node, then this causes a reset, or by sending a malformed packet, or by forcing a reboot of a connected node to let it forge its state, which leads to a reset. So there might be multiple ways per protocol to achieve a reset, and of course the covered receiver needs to monitor these resets somehow. Alright, then let's discuss the storage patterns, and first of all those that are not considering payload. And of these we first highlight structure modifying. So first the size modulation, also one of the early patterns from 2015, where we just modify the size of or modulate the size of network PDUs. And this can be done for essentially all frames and packets and so on. The sequence modulation pattern is also on one of the old patterns, where the covert channel alters the sequence of header or PDU elements, so elements within that header, to encode hidden information. For instance, here you can flip in this HTTP request the order of user agent and accept. So depending on the order, whether user agent or accept language appears first, you encode hidden symbol 1 or 2, but you can also do this with the sequence of DHCP options, FTP commands, and so on, or also with other protocols such as HTTP or and so on, or IP version 4 options, IP version 6 extension headers, and so on. There are two step patterns. So one is the position pattern, where the position of a specific option, for instance, would matter, and the number of elements pattern, where the overall number of options, for instance, would be counted. Note that not the direct, this increases the packet size, but the information is not directly encoded in the size, otherwise it would be size modulation pattern. So this is not size modulation. The add redundancy pattern adds information that is not absolutely necessary, like providing a user agent here in this HTTP 1.0 request. the covert channel creates some new space, some redundant space to put some redundant data that is not really necessary in that context, and hides the data in that. Can also be done by adding a new IP version 60 destination option, or manipulating pointer and length values of the record root option in IP version 4. Now, there are also structure preserving patterns, as mentioned, and the structure preserving patterns are, I think, also the easiest to understand. So sometimes we have a pseudo-random or maybe even real random value that is just overwritten with another random value, like the identifier field in IP, the initial sequence number of TCP, or the XID field in DHCP. So there's a pretty famous covert channel, which is a passive one. So a passive covert channel over ESN. And sorry for my writing. I write this with the mouse, so I have no pen. And let's assume we have an overt sender that is attacked, and the covert sender resides in that overt sender. Now, the overt sender generates TCP packets, for instance, to visit some popular online search engine. And so a flow is generated to some overt destination, which can be our web search engine, overt receiver. Okay. Now, what is done is that there is some initial sequence number in this connection, which is 4 bytes in size, and the covert receiver, however, so there's one proof of concept code called Nushu from Joanna Rutkowska. Nushu, I think it's written like this, and it resides in the Linux kernel and is like a kernel module or kernel patch that translates the original ISN to a faked one. So the original ISN is replaced and overwritten with a covert ISN, which is also random, pseudo-random, but contains the encrypted secret information, so 4 bytes per connection. And on the way to the overt receiver, there must be some gateway that extracts the hidden information again, which is the covert receiver. In the original work, it was found that this channel was detectable because the distribution of ISN values was not matching the one of the original covert channel. Check work by Murdoch and Lewis for this purpose from University of Cambridge from around 2000, I suppose 2010 or so. Okay, so then there is the value modulation pattern, and was also introduced in 2015. It's one of the most common ones. So you can, it's not a random value that we modify, but one value that must be somehow plausible. So we cannot write everything in it. For instance, if we have 10 nodes in an Ethernet network, then we cannot send data plausibly to Ethernet addresses all the time that are randomized and just do not exist. That would be kind of an anomaly. Or it's also not really suitable to select every possible TTL value, because that would be easily detectable. So we need to choose a convincing one that appears legitimate. Some of these channels are not so easy to detect, while others are easy to detect. For instance, this is very untypical if we select an upper or lowercase value for the user agent string to encode different bits. There are 3 sub-patterns. One is the case pattern, which is this one, so we modify the case of letters. Then the LSB pattern is this one, where we modulate the least significant bits of a TTL, or other LSB values, such as the hop limit's least significant bits. Can also be, for instance, be done for the TCP timestamp option. Here in gray is one pattern that is still in discussion, so it's not relevant for the exam. So I strike it here. So the value influencing pattern is one where the covert sender performs some actions to influence the transferred value indirectly. See this paper here for some more information on that. I think the idea is good, but in my opinion, it should not be kept as a real pattern because it's more or less an indirect channel. And as you will see soon when I discuss the revised version of the taxonomy, one would need to split between embedding and representation of the hiding patterns that are applied. Same for the temperature pattern that we've already seen. Okay, reserved unused, we simply override some reserved or unused header fields. Works for several protocols and their fields, so I think this is rather clear. And then we reach the modification of payload finally. And the question was, is this actually feasible? Is this digital media steganography? Because originally we said, okay, this requires some extension, but is this really feasible under the umbrella of network steganography? Well, yes, it is. So it's not necessarily only digital media steganography, and there are two types of patterns here: user data agnostic and user data aware. Agnostic and aware in the same meaning like for the timing channels. What you can do is increasing or in general modulating the payload field size, and you can also blindly override data, which is not really much steganography because it's easy detectable, but it's not really depending on the media so much. You just override the data. You can, if you are aware of the protocol, so you are not acting blindly, you can also modify the redundancy of data using transcoding, for instance. So what is transcoding? In transcoding, let's assume you have a voice over IP transmission and you have some audio packet with some header that is here, and you have some speech data, which is here in the area below. Now, the speech data here uses some compressor, and that compresses, or some audio codec that stores the data here. Now let's assume you can take this data and compress it. So let's say this is compressor 1, and let's assume you reduce the quality and compress the data even more with compressor 2. You take the original speech data and compress it further. What you get would be a packet like this. You still have the header, and you have your speech data, and maybe looks like this. So there is some space that is unused, and this unused space here is replaced then when the packet is forwarded with some secret data. So this is how transcoding can be applied. And then there is PS31, the user data value modulation and reserved unused. Of course, these patterns are derived from some of the patterns we already seen. Let's go back a bit. So payload field size modulation is derived from the size modulation pattern, and the user data value modulation from the value modulation pattern. This is this arrow, and the reserved unused from the reserved unused pattern. So they are linked and at the same time derived from these patterns. We looked at the original 11 patterns and checked how often did they appear, excluding the retransmission, which now did appear much more often, so this heavily increased, but actually all of them increased a lot. So this is just the first 100. For this paper in 2016, we I think analyzed 131 hiding techniques. So And as you can see, most applied value modulation, some form of value modulation. And also interarrival time was rather popular, reserved, unused. These three were also not too uncommon, and some, like random value, despite being very easy to use, were not commonly used. If you want to study essentially the original patterns a little bit more, I wrote a small software that I also refer you to in the exercise. This is a simple tool to play around with patterns. I put sample exercises with solutions on GitHub. I also want to highlight a bit improvements of the taxonomy over the years. So in 2014 and 15, we published this original paper where we defined patterns, proposed the taxonomy, and the first methodology and concepts. Then a year later, that book that I always mention appeared and revised the taxonomy, and then the distributed hiding patterns that I will speak about in chapter 6 were added, and also the idea of hybrid patterns where you apply multiple patterns simultaneously, plus here the end user patterns were for the payload were added. And then this paper here added a new subpattern. These authors applied the taxonomy for information hiding in cyber-physical systems recently. And these two papers each provided a new pattern, the artificial retransmissions and artificial resets. Sorry, this is Reconnections. I will fix this in the slide. Okay. Improvements of terminology. Well, in this paper it was analyzed how patterns can be used during peer review and how one can tell whether a new hiding technique represents, well, a completely new pattern or whether it's a subform or a representation, some more evidence for an existing pattern. Then next thing was for research to be more comparable, one needs a unified method of describing hiding methods, also using patterns, and this was done in this paper here. And then this didactic tool was proposed, and also there is work that shows how patterns can be applied in the context of countermeasures. So many countermeasures exist for covert channels, but they are tailored to one specific hiding technique, which limits their application quite a bit. So countermeasure variation that I will briefly introduce in chapter 7, I think, is a simple process of transferring one countermeasure that is designed for one pattern to another pattern. I excluded several other papers addressing some pattern-related details. Okay, so that was the original network steganography hiding patterns taxonomy. But there was the question of whether this could be enhanced and revised so that it works not just with network steganography but with all forms of steganography, all domains. So that means also the domain of digital media steganography, text or linguistic steganography, file system steganography, cyber-physical systems and IoT steganography, and so on. So a larger consortium was formed with researchers from different domains. So you know me, Luca Caviglione is from CNR in Italy, Wojciech Mazurczyk is also with FernUniversität, but also with the TU, Technical University of Warsaw, Alexandra Mileva from North Macedonian University, Jana Dittmann from the University of Magdeburg, Kevin Kretzer as well, Lemshoft, Vielhauer, and Neubert are also from Brandenburg University of Applied Sciences and Magdeburg University. Laura Hartmann is a PhD student of mine. She's also at FernUni Hagen, and she's also with the Worms University of Applied Sciences, and Jörg Keller is professor in Hagen. So this consortium was formed and revised the taxonomy to identify limitations and address these limitations. Okay, so why was this a good idea? Well, the previous taxonomy, as mentioned, was focused only on network communications and neglected other domains of steganography. And the level of abstraction did not allow the easy inclusion of non-network patterns. So, for instance, user data from the network perspective might be digital media payload, but in digital media, there is often not such a thing as payload. Actually, this is the main part where you hide data in the image. The image is the main object, not the payload to the image. So the distinction was not always clear. And the current taxonomy does not differentiate between the embedding and representation process. So this is a key issue here. So rendering the interpretation of patterns ambiguous. I speak about this on a separate slide. And if such a differentiation would be applied, then some patterns that we already knew would be considered as hybrid patterns, like the temperature pattern or the value influencing pattern. And also, several of the current key concepts were kept, so there were quite some good ideas, and we did not want to reinvent the wheel. We even kept some patterns and just renamed them. Okay, so the distinction between embedding and representation process is meant as follows. So the embedding patterns, so we have embedding and representation patterns, and the embedding patterns describe how secret information is embedded into the cover object, such as an image file or a network packet, while the representation describes how the secret information is represented in the cover object. Because sometimes the embedder has to do something different than the receiver or extractor. So with the temperature pattern, the covert sender, as you will remember, influences the clock screw of some intermediate node, and what it needs to do is sending lots of data or fewer data. So the data rate is modulated over time, but the covered receiver needs to do something different. It might poll the intermediate node many times and measure the request response time. So it does something different than the receiver. So the embedding pattern is this one, and the representation pattern would be this one. There are improved pattern names to make them more domain overlapping. So we kept several of the original concepts as mentioned, but we renamed them to make them broader. For instance, the interpacket timing is a good concept, but what we have are not always packets. It's not interpacket times. It's an interval between events or elements, and we modulate this interval. Or message timing. What is a message? This is somehow an event. And the timing, well, it occurs. So we made this more generic, that it can be applied elsewhere too. We dropped some things like payload and protocol awareness. We skipped to differentiate between syntax and semantics. Previously, one differentiation between structure preserving and structure modification was done. Some patterns can modify both. This goes too deep at this point, but see the paper, for example, where we described the reasoning behind this in detail. We also came up with a glossary to make things more precise, which I will show on one of the next slides. And each pattern name is now also more structured. So there is always an identifier and a pattern name. And the identifier has this form, so it starts with the uppercase letter E or R to indicate whether it's embedding or a representation pattern, followed by T or N to show that it's a temporal or non-temporal pattern, or storage pattern would be also an alternative term, but we decided to use temporal and non-temporal. Then it has a number, and it can have a stegodomain. For instance, n, lowercase n means network steganography, t, text steganography. It fits domain specific. So the pattern RT1T would be a representation pattern that is temporal. Its number would be 1, and it would be text steganography specific. I mentioned improved names, so the names contain the identifier that I mentioned previously, like ET2, and the object and action. So the name contains a modifiable object that could be an event or an element or a feature or an interval or a state and value. And that is followed by an action such as occurrence, modulation, corruption, enumeration, repeating, or positioning. So a typical pattern would be event, occurrence, and here's an overview about the objects that we used. So I start with on the right hand side. So a state or value could be a value in a packet header field, or a number of characters in the text, or a value of a pixel, and that belongs to a feature. For instance, here the value of a packet header field belongs to well, a field of the packet. And that belongs to an element, which is then the whole network packet, for instance, or a text character, or a pixel of an image, and that belongs to an event, like the presence of a flow or a disconnect event, or the occurrence of a character sequence in a text, or occurrence of a predefined sound in an MP3 file. And that can be linked to an interval, like timing between packets, timing between disconnects, things like that. Here you can see the embedding pattern taxonomy, and the representation patterns will be entirely forked and derived from the embedding patterns. So the core thing are the embedding patterns. And as you can see, their number is rather low because we are very generic here. We have only temporal and non-temporal as a category, and we have only 2 major temporal and 5 major non-temporal patterns. Let's go through them and start with the temporal patterns. So we have event and element interval modulation, where the covered message is embedded by modulating the gaps between succeeding events or elements. This is basically the integration of the interpacket gap idea that we've seen already, but you could also modulate time gap between succeeding cyberphysical actions such as acoustic beeps, for instance. And the rate throughput pattern was decided to become a sub-pattern here, because if you send more data per time, then essentially you can also say it's a special form of modulating the interpacket times. The event occurrence pattern is a pattern where the covered message is encoded in the temporal location of the event. So that's like the original message timing pattern. In comparison to ET11, so the rate throughput pattern, the rate of events is not directly modulated, but events are triggered at specific moments in time. So it's not the rate that you measure, but whether a packet, for instance, appears at a specific point in time. Moreover, ET2, so this pattern can be a single event, like one network packet only, while the rate throughput packet needs a sequence of elements. For cyber-physical systems, it could also be the time at which a drone starts, or one could perform a disconnect at a certain point in time. Now let's look at the non-temporal patterns. We have the artificial element loss modulation. You already know the concept here because it's what you've already seen earlier, but you could also, if it's not a network context, remove commas in a sentence, for instance. Element features positioning is also familiar to you. Here the covered message is embedded by modulating the position of a predefined element or set of elements or features in a sequence. So like the position of a HTTP header line and a list of optional header lines, or we could place also a specific character in a paragraph. The element features enumeration pattern is also something that you already seen. Here the covered message is embedded by altering the overall number of appearances of elements or features in a sequence. For instance, we could fragment a network packet into either N or M fragments. We could modulate the number of people wearing a t-shirt in a specific color in an image file, or we could repeat an element or feature by duplicating white space characters or not in a text. And then there's state value modulation. Of course, this was the original value modulation pattern that we modified here, because state can also be a state of a cyberphysical system, like the temperature level of a heater, or heating level of a heater, or the temperature that is measured by a sensor, things like that. So we could modulate cyberphysical states such as proximity, visibility, force, height, acceleration, and so on, or changing values of network packet headers that you already know, or the XYZ coordinates of a player in a 3D multiplayer online game. Pattern has 3 subpatterns. Please refer to the paper. They are rather simple, so I won't go through them here, and they are also, if you go back, they are listed here. So it's what you already seen, basically. Reserved, unused, and random value patterns is the same concept, and blind is just blind overwriting. And same for the next pattern, which is feature structure modulation, where we have the original size modulation plus a new one, which is character feature modulation. But this is really easy to understand if you look at the paper, which I will link in Moodle. So the feature structure modulation modulates the structure of a feature. And this hiding pattern thus comprises all hiding techniques that modulate the structural properties of a feature, but not the states or values, which is the state or value modulation, the position, which is EN2, or the number of appearances, which is EN3. So what remains is, for instance, increasing or decreasing the size of succeeding network packets, which was the size modulation, or changing the color and style of characters in text, which would be the character feature modulation here. Alrighty, and then so while the embedding patterns are generic, we can derive specific domain-specific patterns as well, and also the representation patterns, as we can see here. So let's zoom in. These are the network steganography patterns, and essentially they are just the same as the embedding patterns. If they are domain specific, then you see the domain indicator, which is the lowercase n here for the network steganography domain. However, there are some specific derivations which I kept in bold font here. So a special type of event that occurs is a frame corruption. So this became a sub-pattern that is specific for the network domain. And also a specific type of artificial element loss is a forced reconnections modulation, because you lose the reconnection. One would more or less likely add one day the artificial resets here as a RN 1.2n. But that's up to be decided by the whole community, and I won't do this by myself until it's agreed upon in the community. And another form, a special form of elements features enumeration, would be the artificial retransmissions. So these are the current representation patterns for the network steganography domain. More information about this revised taxonomy you can find on patterns.ztths-worms.de. If you click on About, you get a short summary. You can find the pattern collection here. Also, I uploaded a video lecture that is more or less identical with this one from the conference talk, extended version of the 2021 August talk at the ARES conference that I gave. Some final remarks. Is it better to find a new hiding pattern, or is it better to improve the existing hiding methods and to study them? Because we first need to understand always what kind of hiding methods are feasible before we can develop countermeasures. But in the end, both is important and should be done. However, simply applying an existing method to some other network protocol without presenting a new pattern or an improvement over an existing work is less creative. I will discuss details of this in chapter 9. Actually, creativity is a term that is not here by accident. It's actually a scientific term and depends on two aspects, namely novelty and applicability of an idea. I also ask this question from a research point of view. So if you want to publish some scientific paper, for instance during a PhD, about hiding methods, then it's it's better to have a new pattern, but it's also extremely important to study in detail the existing methods. Well, I mean, the research gaps are everywhere. Okay. So there are currently two hiding pattern taxonomies. One is specific to network steganography with discussed limitations, and there is a revised taxonomy for all steganography domains. The revised taxonomy addressed several limitations, especially improved again terminology and systematic of pattern enumeration. It's more general because it can be applied to all stegodomains, not just to network stego. It kept the good concepts and pattern ideas of existing terminology, so we did not reinvent the wheel when not necessary, and we also didn't want that because the original taxonomy received about 133, I think today I checked, was 133 citations. So this word should be citations. So this is quite a bit for a scientific publication. That means that this existing taxonomy is widely accepted, and it should not be neglected entirely, because otherwise we again get an inconsistency that is larger than it should be between the old and the new taxonomy. So the thing is that the network steganography specific taxonomy is still fine, but one should use the network hiding patterns in a way that it's different, that one differentiates between the embedding and receiving process. So this is one of the things that I said during this lecture. It's probably the main reason for this network specific taxonomy and its main limitation. So one really should describe what is done by the embedding and what is done by the representation process or extraction process. Current research work of the scientific community is that the representation patterns are currently in process to be defined for digital media, text, file system, and CPS steganography. And there's also discussion whether this taxonomy would be applicable somehow to digital watermarking, so that digital watermarking could potentially be also integrated into the taxonomy. Then it would not just be a steganography taxonomy, but one also for digital watermarking. All right, that's all for this lecture, and thank you very much for your kind attention.